All right, so any questions? Homework or whatever.
Are you going to get a slice of pie today?
I think I might.
Will it be a whole pie or half a pie?
It's going to be a really tiny slice of pie. Because pie's not on my food plan, but it is pie day.
The argument I always hear is a whole pie is actually 2 pie.
No, see,
yeah.
It's a circle.
No, see, you go to July 28th and you get 2 pie for Tau Day.
Oh, nice.
There you go.
So Pi Day and Einstein's birthday and the day Stephen Hawking died. Really sad. So, but yeah, lots of stuff. Questions? All right, let's look at Dijkstra's algorithm. So Dijkstra's algorithm is a way to find a shortest path through a weighted graph from one point to another. And let's make a sample. So our goal, find a shortest path from A to F. And the detail we mentioned yesterday is it's not always going to be the path with the shortest number of edges, right? If we just want the fewest number of edges, we can just go B, D, F, and we're done. 3 hops, or we could go C, E, F, and we're done. But in fact, by taking a path that includes B, C, and maybe D, E, we may do better. Right? For example, from D, we can get to F directly through an edge of length 6, or less directly through an edge of length 2 and an edge of length 3. So once we get to D, this is going to be a shorter path. And trying to find a shortest path is a tricky proposition. It's not something that works well with a greedy algorithm, right? Obviously, we could have one city here that's very close to A, but then really, really far from everything else. And if we greedily went to that city first because that was the shortest hop, then we'd be suboptimal. So Dijkstra's algorithm is a loop, and it's got a couple of steps, and we just keep iterating on these. So we're going to start with city A. So step 1, visit your starting node, which I'm going to just say circle it. Step 2, mark all nodes with their tentative distance from starting node. All right, so what does this mean? We're starting at A. What's the distance from A to A? Well, that's going to be 0. Okay, we don't have to travel anywhere because we're already at A. But every other node, we want to say, what's the shortest guaranteed distance that will get us from A to that node? And we haven't done any work yet. So initially, the shortest distance that we can guarantee to each node is infinity. So we're going to mark those distances. And it means we know we can get there in an infinite amount of steps. But hopefully we'll be able to do better. All right, so mark the tentative distances from the starting node. Those are all infinity. All right, find the closest node to any visited node. And by closest node, I mean connected by a single edge. Well, the only node we visited so far is A, and so there's only two nodes that are directly connected to us, B with a distance of 4 and C with a distance of 2. Okay, so C is going to be the closest node. So we're going to say visit that node. Which means circle it. Update its distance. Well, how do we update its distance? We know that we can get to node A with a distance of 0. And we know that from node A, we can travel a distance of 2 to get to C. That may not be the shortest path to C, but we know that we can get to C from A with a distance no worse than 2. So we're going to update its distance and say that's a distance of 2. I forgot something. I'm going to need to throw a step 2.5 in here. Let's do it like this. So visit your starting node. Mark all nodes with tentative distances from starting node. Okay, let's throw a different step in here. It's going to do the same thing here, but let's not circle this. All right, so this is what we call relaxation. So we're going to do what's called relaxing all the nodes connected to the node we just visited. So this means we started off with node A, that was our visited node. We're going to do what we just did. We're observing that we can get to node A with a distance of 0, and a distance of 2 from there will get us to node C. So we know we can get to node C with a distance of 2. Since that's shorter than infinity, we're going to mark this distance to be 2. That's the relaxation part. And similarly, from node A, we can travel a distance 4 to B. So we know we can reach B with a distance of 4. And that's better than infinity, so we're going to relax that distance down to a 4. Okay, so now we're going to say find the closest unvisited node. So the only node we visited so far is A. So this has a distance of 2 from A, this has a distance of 4, these have a distance of infinity, so C is our closest node. So we're going to visit that node. So circle it. And then we're just going to keep repeating these 2 steps. Okay, so we visited the 2. We want to relax all the nodes connected to 2. Okay, how does this work? Well, we can get here in a distance of 2, and another 10 will get us to E. That means we can get to E in 12. That's better than infinity, so we relax that node. We can get to C in 2, and another 8 gets us to D. That's 10. That's also better than infinity. We relax that node. And 2 plus 1 means we can reach B in a distance of 3, which is better than 4. So we're going to relax that node. All right, step 4, find the closest unvisited node and circle it. So we've got a node of distance 3, 10, 12, and infinity. 3 is our closest to A, so we're going to mark that. And then we're going to relax all the nodes that are directly connected to B. So C we've already visited. We don't have to do anything with it. D is connected to B with a distance of 5. Well, we can get to B in a distance 3, and 5 more is 8. That's better than 10. So we're going to relax that. And that's it. Those are the only nodes connected to B. Once we've visited a node and we've marked it, we know that that's the best distance to that node. So we don't need to do anything to those visited nodes again. All right, step 4, find the closest unvisited node. Well, we've got an 8, a 12, and an infinity. This is going to be our closest for 8. And now we want to relax nodes again. So 8 plus 2 is 10. That's even better than 12. 8 plus 6 is 14. That's better than infinity. So there's the relaxation of the nodes. And now find the closest node that's not visited. That's going to be a distance of 10. So we'll visit that and we'll relax adjacent nodes. So 10 plus 3 is 13. That's better than 14. And that's the only unvisited node. So find the closest unvisited node. There's only one node left, which is F. And that's the node we're trying to reach to. So the shortest distance from A to F is 13.
So what are the distance between A and B was 3, and the distance between C and B was 2.
So
between A and B was 3.
let's try it. All right, so A and B is
3.
3.
Yes, and between C and B is 2.
C and B is
And
2.
you keep everything else the same.
And everything else is the same. Okay, cool.
In that case, the theorem wouldn't really work because we'd be doing one extra move or one extra distance.
All right, so we're going to start at A. We're going to mark tentative distances. So infinity, infinity everywhere. All right, so relax all the nodes that are adjacent to A. So this will become a 3, and this will become a 2. And then we find the closest node, that's going to be C. So we'll visit that. We can relax, well 2 plus 2 is 4, that's not better than 3, so we're not going to change that 3. 2 plus 8 is 10, and 2 plus 10 is 12. And then find the closest node, that's going to be B. Relax, 3 plus 5 is 8, and that's the only node connected. Closest node is 8. Relax from there, 8 and 2 is 10, 8 and 6 is 14. 10 is the closest. Relax from there, 10 and 3 is 13. And then that's the closest. All right, so is that not an optimal solution? So it looks like we went like that. Could we have done better?
Well, I know that's the best path from D to F, right? And I think that's the best path from A to D, so I think that's the best path from D to F.
this would be 2 and 8 is 10, 2 and 2 and 5 is 9, 3 and 5 is 8. I think that's the shortest.
When it says find the closest node, is that the closest node to the one you just visited or to the starting node?
Closest node from A in this case. So these distances we're writing in are distances from A. So you find the node with the shortest distance from A.
So basically the shortest marked number.
Yeah, with the smallest number.
So why would you go to B if it's 3 and C if it's 2? Like I know, I mean in like that immediate decision in the beginning, because like later on you can see that it's 4 to go up.
Yeah, so initially we went to C, right? That was the first node we visited after A, because that was the shortest distance. But eventually, well, so let's talk about how to keep track of the paths, because I think that's the question here. So let's redraw this with more space. So in addition to keeping track of the distance, we also want to keep a list of the nodes that got us there. So we're going to put in tentative distances. And this is going to have a distance of 0. We're going to visit A initially. And I'm also going to write down next to the distance the path that gives us that distance. This is a little PA5-ish, right? So the shortest path from A to A is just A, right? And it's got a distance of 0. That's just an edge. All right, so let's run the algorithm again. So which node, so relax the nodes, okay? So this will have distance of 2. And the way we get there is going through A. And this will have a distance of 3. And the way we get there is going through A. And all the other nodes are still infinity. So now we know we can get to this starting at A and coming to C, or starting at A and going to B. So now we find the node that's closest to A, that's our 2. So we visit this. Yeah?
What's distant from D to E?
D to E. Oh, good question. 2. Thanks. All right, so we visit C. We mark that. Now we want to relax nodes from C. So from C, we can get to E in a length of 10. 10 plus 2 is 12. That's better than infinity. So we change the distance to 12, and we record the path. So what was the path? Well, it's whatever path we needed to get to C, which was just A, plus the node that we're coming from, C. And to get to D, we can go 2 plus 8 is 10. That's better than infinity. So we'll mark this as 10, and our path will be the path to C, followed by node C. And here we can go 2 plus 2, did I miss something up? 2 plus 2 is 4, right? And 4 is not shorter than 3. So we don't relax that node, we don't change the path. Okay, so that's where that path from A is coming from. All right, so now pick the node that's closest to A, that's B, and relax from there. So 3 plus 5 is 8, that's better. So a distance of 8, and the path is A, followed by B. So the path update is always just the path to this node followed by this node, right? Here's 2 plus 10, we already did that, we're relaxing from B. Okay, that's the only thing we can relax. Find the closest node, that's D. We'll relax from D, so 8 plus 6 is 14, that's better. And the path is A, B, followed by D. And 8 plus 2 is 10, that's better than 12, so forget that path. We can do a distance of 10, and the path is AB, followed by D. Now 10 is our closest node, so we'll visit E. And 10 plus 3 is 13, that's better than 14. And the path is the path to E, which was A, B, D, followed by E. And now 13 is the only unvisited, so that's the shortest distance, and we're done. And so a shortest path from A to F will be A, B, D, E, and then F. You could put in the B here and the C here and the D here. It depends how you're doing it, but I know that that node's always the last step of the path. So that's the shortest path. So A, B, D, E, and then F. So how do you code this? Well, you need your graph stored somehow in your memory, right? And we've got multiple ways to do that. But what kinds of things are we trying to do? We're trying to find, given a particular vertex, we want to find the distance to any connected vertex and then pick the smallest of that. Well, not exactly. We want to find the connected vertex with the shortest visited distance, right? So we need to augment this. We need a matrix of something like a structure maybe, or maybe parallel matrices, where the matrix will tell us what's connected to what the expense of that connection is, but also store information about those vertices. So you might have something like a 2D matrix. And so on. So when we're relaxing nodes, right? If we're relaxing from, say, node C, we can simply find all the nodes that are connected to it, so everything that's not 0. And for each of those, we have to go through some kind of array. Which has minimum distance and some way to represent the path that gets you that. So if we're relaxing from, say, C, we come over here, we find every node that it's connected to, take the distance to that node, add the minimum distance to that node, and compare it to the recorded minimum distance, and if it's smaller, update it, right, relax it, and also update the path. It's not hard, it's housekeeping, right? So we may do this in 223, because once we've got objects in our toolkit, it's nice to code stuff like this. So this is pretty efficient. It's orderish, and I believe maybe n squared worst case. If you have a lot of connectivity at each step, you might have n nodes to consider. So it might be n squared, but it's definitely poly. It does not work if you have negative weights though, which is kind of interesting. This assumes all your weights are positive. If you have negative weights, the algorithm breaks down. And I'll let you think about why that might be.
So because the weight of A is always going to be 0, then you have like the weights from like A to B and A to C both be negative, and you can't get an F because 0 is greater than negative number.
Yeah, there's a greedy component to this, right? Once we found the closest distance from a visited node, right? We know at that point that we're not going to do better than say 3 to node B, right? But if we had some really expensive path over to here, and then some ridiculously huge path over to here, and then this really, really, really big negative weighted path over to here, which might bring the total cost down to like 1 or 2, right? That would be more optimal than this. But we'd have no reason to explore that until we eventually got out to these ridiculously long paths. Because that negative contribution is at the end of that pathway. So it just doesn't work. It's not too bad to sort of wave your brain at this and convince yourself that this actually works with positive weights. But a formal proof is a little complex. But as you do that, if you think about negative weights, then you see these kinds of issues. All right, so you think you got Dijkstra's algorithm? So here's what we're gonna do. Going to have you put yourself into groups and find a spot on a whiteboard. And I'm gonna stop recording. And you're going to do your last part of your homework assignment.
I'm not going to know what you're going to grade then?
This is the one I'm going to grade.
Oh.
Ha, didn't see that coming, did you? Well, I'm always generous, right?
Going for those remember that's
Yeah.
Or he'll have it work in class and then he'll change it on the homework assignment. See what we do.
All right, so that's your problem. Let's use Dijkstra's algorithm and find a shortest path there and break yourself into groups, right? And I want everybody to try to make sure you understand this. And then I want you to turn in all your homework, okay? And I'm going to make sure you've done all of the problems, right? And I'll take off if you haven't, but this is the one that's going to count the most points. So you're going to want to write this up neatly, and this will be a chance to figure out what it should look like, okay? So go ahead and work on this in groups on the board right now, and then include it in your homework, but include the others as well.
So when it says redrawn a graph,